Alright, problem-solving strategies. Problems can sometimes seem like this huge rock or this huge weight that you can't deal with. Well, hopefully at the end of this lesson, you will begin to view problems as just a bunch of puzzle pieces that need to be put together in the right way. Alright, so 3 steps I want you guys to consider when you're solving a problem. First step, when in doubt, draw it out. Draw a picture. Second thing, make a table and or look for some patterns. And lastly, we want to check our answer. And if possible, we want to plug that answer back in, or we want to find another way. Alright, let's put those 3 steps into practice. Our first example, how many diagonals does an octagon have? Alright, well it says when in doubt, draw it out for our first step. So I'm going to go ahead and draw an octagon. Octagon means 8 sides, think octopus. And that's pretty good. And I'm going to go ahead and label each of the vertices. I'm going to label them alphabetically A, B, C all the way through. So all 8 points, E, F, G, and H. And I'm going to use different colors to show these diagonals. Now if you recall, a diagonal is just a line drawn inside the figure from one vertex to another. So I could go from A to C, from A to D, A to E, A to F, A to G, and that's 1, 2, 3, 4, 5 different ways I can do it drawn from A. I'm going to make a table while I go because I want to do it drawn from B, drawn from C, etc. So my table looks like this. I have the vertex and the number of diagonals. So my first vertex was A, and I got 5 diagonals from that. Now I'm going to start from B, and I can go from B to D, B to E, B to F, B to G, and B to H. And notice none of those were the same as the ones drawn from A. Because if I connect B to A, that's not a diagonal, that's an actual side on my octagon. So I have for B, I'm going to have 5 again. Let me start from C and see if I can get a pattern going. I can go from C to A. Wait, I've already used that one, so I don't count that one. I could go from C to H, that's new. C to G, that's new. C to F, and C to E, and then C to D is a side, so I don't use that. So even though I have 5 diagonals, I've already counted the A to C one, so I don't count that one again, because that was already counted with my black diagonal. So there's only 4 unique ones for C, or there are only 4. Alright, I'm going to use a different color now from D. And notice D to B, whoops, I've already used B to D, or D to B, so I'm not going to count that one. I've already used D to A, see that black line I already had? So I'm not going to count that one. D to H is new, D to G is new, and D to F is new. So if I start with D, now I only have 3. And you probably start to see a pattern forming, don't you? And we'll go ahead and prove it. So now if I start from E, I've already used the E to C, so that doesn't count. I've already used the E to B, so that doesn't count. I've already used E to A, that doesn't count. But I haven't used E to H, E to G, and E to F is a side, so that's only 2 unique ones for E. See the pattern? It goes 4, 3, 2. You can predict that F is going to be 1, right? Let's just prove that. So F, I've already used. F to D, that doesn't count. F to C I've used, that doesn't count. F to B I've already used. F to A I've already used, but I have not used F to H. So F gives us 1. And then G, you can just look at G. G already has everything going from it. So I already have G to A is used, G to B is used, G to C is used, G to D is used, G to E is used. So there's nothing for G, so G is just going to be 0. Alright. Well, we want the total number of diagonals, because it says how many diagonals does an octagon have. So the total is just add all these up. So 5 plus 5 is 10, 14, 17, 19, 20. So our total number of diagonals is 20. And us drawing our picture was step 1. Us making the table and looking for patterns was step 2. What do you think step 3 would look like to check our answer? Is there another way we could have done that? Because that was a lot of lines being drawn right there. Maybe there's an easier way. What if I started with a smaller figure, like a triangle, and counted the number of diagonals? And then moved up to a quadrilateral and counted. So I'm going to make a table with the number of sides and the number of diagonals. So for instance, if we had a 3-sided figure or a triangle, I'm going to draw that. And that's not a diagonal, that's not a diagonal because it's the same side. So there are no diagonals in a triangle. But what if I bump up to a quadrilateral, like a rectangle? I could draw from this vertex to that vertex, or from this vertex to that vertex. And there to there is the same thing, there to there is the same thing. So there's only two, or there are only 2 unique diagonals. Alright. Well, what if I go to 5? And a 5-sided figure is a pentagon. So here's my pentagon. I'm going to start from this vertex, and there's 1, there's 2. I'm going to use a different color now if I start from there. So there's 1, there's 2, so that's a total of 4 now. And then if I start from this one, I could go there. Oh, I've already used that one. That doesn't count. But that one's unique. And then if I start from over here, I've already used that one and that one. So there are no more unique ones to pick from. So count those up. We had 2 blues, 2 reds, and a gray. So that's a total of 5. Do you see a pattern developing? I went from 0 to 2, then from 2 to 5. Well, I'm not adding the same thing every time, but I could be adding 2 and then 3. What do you think we're adding next? 4? Let's see if that's true. Let's go one more and see if that proves our point. So let's try a 6-sided figure, and that would be a hexagon. And again, I'm just going to start from one vertex, so let's start from that one. So there's 1, 2, 3. And then starting from here, I have 1, 2, 3. So that's a total of 6. And now I've already used that one, so that one doesn't count. That one's new, so 7, 8. And now I'm going to use a different color. Let's try orange. I've already used that one, I've used that one, so those don't count, but this one's going to be new. And if you look from that next point, that next vertex, I've already used everything coming from this one. So I've used that, I've used that, I've used that. So those are not unique. So I'm just going to count 3 blues, 3 reds, 2 greens, that's 8, plus an orange, that's 9. So yeah, our pattern worked. So 2, 3, 4. Now if we add it again, we're adding one more each time. So if we add 5, we would be up to 14 for a 7-sided figure. For an 8-sided figure, what would I need to add? That's right, 6. So 14 plus 6 is 20. Ding, 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 ding. We had 20 there. We had 20 over there. So our check method worked. We tried it a different way, and it worked out. All right, let's try one more problem. And every problem we're going to solve like this. We're going to try to draw a picture, try to make sense of it, try to look for simpler patterns, and build on prior knowledge. Okay? So here's our next problem. All right, copy down example 2. Find the sum of the interior angle measures of a hexagon. And again, you're going to find out this is just another puzzle or another problem that we know enough information to solve. We just need to find the right pieces. So I'm going to break this down for my first step. So I'm going to draw it out. So let's draw a hexagon. That's 6 sides. And hopefully yours looks a little better than mine. Alright, I made mine look a little better. You made me paranoid. Alright, sum. First off, the word sum means add. Interior means inside. And I know hexagon has 6 sides. So right now I'm kind of drawing out or defining everything in my question to make sure I understand it. And there's one more thing. I do know the degree measurement of a triangle. So that's something I want to add to this. A triangle has 180 degrees for the inside angles, or the interior angles. And that's good to know. So how many triangles could I make out of this hexagon? We just talked about diagonals, so I could draw, there's one triangle, there's another triangle, there's another triangle. So doesn't it stand to reason that I could make 1, 2, 3, 4 triangles out of this hexagon? And notice that these have to be drawn from one vertex. They must be drawn from one vertex. Otherwise, we could have a ton of triangles, which we know is not true. Must be drawn from one vertex. Alright, so we do know a 3-sided figure. I'm going to make a table now and see if this makes sense. And actually, this is kind of like our step 3, because we're checking it. We basically just did our 2 steps. We found a pattern, and now we're just checking it a different way. So 3 sides we already know has 180 degrees, because that's one triangle. But what if we had 4 sides? What do we know that's a 4-sided figure? A quadrilateral, right? And we just learned that rectangles have 4 90-degree angles. Well, let's build from that. 4 times 90, yeah, it gives us 360. Well, how many triangles is that? Well, we said one triangle is 180, so 180 plus 180 is the same thing as 4 times 90, isn't it? They both equal 360. So far, our idea is panning out. That's 2 triangles. Well, if that's true, a 5-sided figure should have 3 triangles. Let's see if that's true. And actually, I'm going to go back to my rectangle. If I just start from one vertex, I have 1, 2 triangles. So yeah, that worked. I'm going to draw a pentagon now, a 5-sided figure. And let's count from there. Just from one vertex, I can make one triangle there, two, so there's 1, 2, 3 triangles. And 3 times 180 gives us 540 degrees. And let's see if that proves our point for the six-sided figure, our hexagon. Well, we just did that up there. We drew our picture up here, and that made 4 unique triangles. So that would be 720 degrees would be 4 triangles. And now I'm just going to ask you, do you see a pattern developing with the number of sides and the number of triangles? That has 3 sides, 1 triangle, 4 sides, 2 triangles, 5 sides, 3 triangles, 6 sides, 4 triangles. Yeah, you should be able to see a pattern there, so that the number of triangles is 2 less than the number of sides. Which leads us that there's a formula, n minus 2 times 180, where n is the number of sides. But I think it's much better to learn that visually and just count the triangles. But you can always fall back on that formula if you want. N minus 2 times 180 gives us the number of sides. All right. So problem, one piece at a time.